Hello guys, in this very lesson on chemistry, we're going to be discussing a new topic known as balancing chemical equations. So there are two major keywords. I'll share this very topic into two major keywords, which are balancing and chemical equations. So when we talk about chemical equation, what is a chemical equation? That's the first thing we're going to look at. So a chemical equation is the representation, is a representation of reacting chemicals, is a representation of reacting chemicals or reacting chemical substances and their products using, look how we're going to be using chemical symbols. Using chemical symbols. So when we talk about chemical equation, there's the first keyword, the first major keyword we are discussing. A chemical equation is simply the representation of reactant chemical substances and their product using chemical symbols. It's very important to stay focused on these chemical symbols. That is, without the chemical symbols, there is nothing like chemical equations. For example, if I have A plus B, these two are reactants, giving us C plus D. The A plus B, we call them reactants. These are the chemical, substances that come together to give us these two known as the product. So A plus B will give us C plus D. So this A, B, C, and D, I can call them chemical, symbols that represent these various chemical substances or compounds. So that's that for chemical equations. So we're going to be discussing the balancing part, which is, the other part. The major part is the chemical equations. So before we go into this fully, there are two major things we're going to be discussing. First of all, we're going to be discussing the history of, chemical equations. How did we arrive at chemical, equations? So the next thing we're going to be discussing, we're going to be discussing the classifications of chemical equations. So first of all, let's start with the history. In our previous lesson, we talked about, the various set of scientists that worked on the various laws of chemical combination. And so we're going to be just running through them quickly again. And after that, we're going to look at the major scientists, the major chemists that brought about the invention of these various chemical, symbols that we use to represent different chemical substances. So there's a timeline. So we are looking at the history of all this, how we arrived at this. Everything started with this Russian chemist known as Mikhail Lomonosov. Mikhail Lomonosov was the first chemist in the year 1748. This very Russian chemist worked on the law of conservation of matter. He started everything. He started with this very man. So he worked on the law of conservation of matter. So after that, there's a Russian chemist. After that, we have the next chemist known as Antoine Lavoisier. Antoine Lavoisier was a French chemist. So 41 years after the great work by Mikhail Lomonosov, Antoine Lavoisier came up, he worked more on the whole thing that Mikhail Lomonosov started. So that's in 1789. He did a wonderful work also on the law of conservation of matter. They both work on law of conservation of matter, or law of indestructibility of matter. These two great scientists. And after Antoine Lavoisier, the French and chemist or scientist, the next scientist we have is a German chemist known as Benjamin Richter. Benjamin Richter was the next chemist that we have that worked on. Others people worked on the various laws of chemical combinations. We discussed this in our previous lesson. So just 2 years after the work of Antoine Lavoisier, that's 1791, and this man worked on the law of reciprocal proportion. He worked on the law of reciprocal proportion. And after that, we have the next scientist. That's about, the next scientist we have, that's about 10 years after the great work of Antoine Lavoisier, came this very scientist. That's 8 years after this man's work. And that is the person of Joseph Proust. Joseph Proust also was a French chemist. This man also was a French chemist. This is a German. So Joseph Proust in 1799 brought about, invented the law of constant composition or definite proportion, law of constant composition. And after the great work of Joseph Proust, the next scientist, this very scientist, a very popular one, is an English scientist, and that is the person of John Dalton, the great John Dalton. John Dalton spent a couple of years between 1803 when he started this work to 1808 when he officially put it out. It was one that worked on the law of multiple proportion. Dalton worked on the law of multiple proportion. So this great set of scientists worked on various laws of chemical combinations. As you can see, from Michael Lomonosov that started the whole journey, down to John Dalton that did a very beautiful work, on law of multiple proportion. So all the set of scientists did great works, but there's one more scientist that we're going to discuss today, and that's a Swedish scientist by the name. I'm just going to add it to this list. The Swedish scientist by the name Jöns Jacob Berzelius. So Berzelius was, and say this very man was a major man that brought about the chemical symbols we're going to be discussing today. This chemical symbols was invented mainly by Jöns Jacob Berzelius, and he started working on this in the year 1811, just about 3 major years after Dalton put out his work on law of multiple proportion. So Berzelius did a whole lot of job. He weighed different elements, and also he was able to bring out better chemical symbols, to represent various chemical substances. Before Berzelius came on board, there was no proper visual, representation of these various chemical substances. Scientists could not really, write out or write down these chemical substances reacting on paper. It wasn't possible, even regardless of the fact that John Dalton had what we call images. I'm going to be showing you the various images, that represented various chemical substances during John Dalton's time, and we're going to compare it with Jöns Jacob Berzelius' work. Everything started with this very man, Jöns Jacob Berzelius, in 1811. If not for his work, there's no way we're going to have a chemical equations talking of balancing, this very chemical equation. So we're going to take off this portion of the board, and we're going to look at the major differences, between John Dalton's images and Jöns Jacob Berzelius' symbols. So quickly, let's take up this very portion. So don't forget, we're still talking about the history of chemical equations. We're talking about how we arrived at this, then before we go directly to classifications. So right here, this one we have right here. So these are John Dalton's images. These images came from John Dalton, and all these are Berzelius. So Berzelius symbols. So before Berzelius came came on board, John Dalton had different images. I'll call it images because they were not symbols actually. So he had various images representing various elements. So for example, Dalton hydrogen was written like this, a circle with a dot at the middle. And we have, just write a couple of them. You have oxygen. Oxygen was just a plain circle. Then we have carbon. We have carbon. Carbon, a circle that has been shaded like this, shaded up. Then we have nitrogen. These were the symbols, early symbols that scientists were using. Dalton's images, I mean. So we have a circle with this sword in it, this cross. Then we have a sulfur. For sulfur, we have this for sulfur. And we have just a couple more like that. Dalton used these circular images to represent various chemical, elements. But when Berzelius came on board, he used proper symbols that we use now. The symbols, according to IUPAC, that is being used in chemistry, was invented by Jöns and Berzelius. So let's see Berzelius symbols. For hydrogen, for example, hydrogen, according to Berzelius, is H. Then oxygen, according to Baselius, is just O. Then carbon, according to Baselius, is C. The nitrogen, according to Baselius, nitrogen is N. Then sulfur, according to Baselius, is S. So you have a whole lot more of of various John Dalton's chemical images representing elements, and that of Baselius also. So just imagine back then, if let's say the chemical compound like water H2O was to be written, H2O was written like this. We have two atoms of hydrogen, which is this. Don't forget, just like this. We have hydrogen connected with another hydrogen, then with one oxygen. So this was how John Dalton, would write out his own very given, chemical symbol for a given chemical like water H2O, for a given compound. I mean, H2O. Look at this Dalton's work. But H2O here, this is John Baselius' work. So you can try to have a comparison between the two. Baselius used symbols, hydrogen, that's H, oxygen O, but Dalton used images. You can see there's two atoms of hydrogen and one atom of oxygen. So after the wonderful works by the set of scientists that we discussed earlier, John Jacob Baselius came on board to bring about symbols to represent various chemical elements. So if not for the wonderful work of this very man, there's no way we're going to be discussing chemical equations because it's not feasible trying to write out a chemical equation using John Dalton's images. For example, H2O reacting with another element would make any sense. So that's that for the history of chemical equations. So quickly we are going right away to the various classifications of chemical equations. Okay, guys, quickly let's look at the various classification of chemical equations. When we talk about chemical equations, what are the various kinds of chemical equations? Now, chemical equations are divided into two major kinds, which are what we call the non-redox. Redox is reduction, oxidation. The non-redox, equation, chemical equation. The non-redox equation, and then the redox equation. So when we talk about redox, we're talking about reduction, oxidation. Reduction, oxidation. We're going to be discussing more of that when it's time for us to discuss, redox equation in proper. So we have what we call the non-redox chemical equation, or we can call it simple stoichiometry equation. So this is non-redox, or just the simple stoichiometry equation, or the redox equation. So what are the major differences between them? We discussed already. We discussed the various history of this, and we are looking right away at the types or the classification of equations. So you're going to be seeing the differences between these two forms of equation. So because once we're done with this in the next lesson, we're going to be balancing the various chemical equations. So the first is the non-redox chemical equation, and that over there. So what are the major differences? When we talk about a non-redox or a simple stoichiometry, chemical equation. What are we talking about? We're talking about a kind of equation whereby there is a transfer of ions. Now that's the first thing. Ions are transferred. For this very equation, what is transferred is ions. I'm going to be giving you an example to buttress this, to explain this proper. Why this electrons are transferred for the redox equation. Here there is a transfer of ions, while here there's a transfer of electrons. So let's have a simple example. I'm going to be using what we call an acid-base neutralization reaction, or we can use the precipitation reaction. So if we use an acid-base neutralization reaction, we have something like, let's say, HCl, a conch HCl plus sodium hydroxide, which are both aqueous. When they react, we have sodium chloride plus H2O water. Now look at what we have right here on the board. Now this is a non-redox equation. It's a non-redox chemical equation. Now let's see why it's non-redox. Now when you look at this hydrogen here is positive. This is a positively charged ion. This is negatively charged. This positively charged. This negatively charged. OH minus, Na plus, H plus, Cl minus. Now when these two chemical substances react together, what happens? They transfer the ions. Ions are transferred. Hydrogen, which is positive, goes with negative OH, that's hydroxyl ion, while chlorine goes with the sodium. And that's why we end up having sodium chloride, which is a salt, and H2O, which is water. So this is simply a transfer of ions. This very positive ion replaces the chlorine ion with this. So H goes with H2, with OH, I mean, to form H2O, which is water, while chlorine goes with sodium to give us the salt, which is sodium chloride. So there's a very good, example of a non-redox and chemical reaction. That's the first thing we're going to be looking at. There is a transfer of ions. Ions are transferred. It's a kind of exchange. Let me use that word of ions. This very positive ion goes with this very negative ion, while this goes with this. Why for the redox equation there is a transfer of electrons. Let me just write out something simple here. The sodium plus chlorine gas, which will give us excess sodium chloride. I'm going to balance this off. We have two right here. So when we have this, what are we talking about here? If you look at the sodium, this when it comes to redox equation, ions are not really being transferred. We're not talking about transfer of ion like this. It's not like a swap of ions. What we are talking about is there is a transfer of electron. Electron is being given and electron is being received. And that's why we call it a redox reaction. Now, when you look at this, we're going to be talking more about this when it's time to discuss this, really when it's time to balance this set of equations. So for sodium, sodium has what do we call it? Sodium right here, we have oxidation number of 0. Chlorine here also oxidation number of 0. According to a rule in chemistry, every atom of a given element can be called a virgin atom. Let me use that word. Is neutral. Is not positively charged or negatively charged until there's an interaction with another atom of another element. So sodium here is 0, chlorine here is 0. Without they reacting, they are just 0, regardless of the amount of atoms they have. So after reacting, we end up with sodium chloride. It's more or less like formation reaction, or other kind of reaction like decomposition reaction on that redox equation. So sodium is 0, chlorine is 0. Right here, we end up having sodium to be +1, while chlorine here is -1. And what do we have here? This was 0 here on the reactant side. All of a sudden, we have +1. That means there's an increment in oxidation number. So what does that mean? It means that sodium, the way sodium is here, sodium gave out 1 electron. If a given atom of element gives away electron, that very atom of element becomes positively charged. We call that oxidation. That atom of element becomes oxidized. That very element is a reducing agent. Most metals are reducing agents. So sodium that is 0 gives out 1 electron to become electropositive sodium, +1. While chlorine that was 0 here, you can see chlorine 0 here. What happens to chlorine all of a sudden reduced to -1. So chlorine gained 1 electron from being nothing to gaining 1. So once you gain an electron, you become electronegative. So chlorine here is, as you can see, 1 minus or -1. So that's that. So when it comes to redox equations, electrons are exchanged, electrons are transferred, as you can see. We don't have search for non-redox equation. For non-redox equation, instead of us to have an exchange of electron, we end up with exchange of ions, just swapping of the ions. So there's the first major difference between the non-redox equation and the redox equation. So the next we're going to be looking at is simply this. Ions are transferred, electrons are not transferred. The next is masses are balanced according to the law of conservation of matter. Very, very important. According to that very law by Antoine Lavoisier, masses are balanced. And when it comes to non-redox equations, we make sure that the masses of the chemical substances reacting and even the product achieved or gotten will balance out everything. And we're going to be using this as a very good example. When you look at this, hydrogen plus chlorine, hydrogen chloride plus sodium hydroxide, giving us sodium chloride plus H2O. We're going to make sure that if this is going to be an equation, actually, if what is here on the reactant is going to be equal to what is here on the product side, it means the masses involved must be balanced. That is what the non-redox reaction is all about. For the non-redox reaction, we are only focused on how to balance the masses of the reacting substances. So hydrogen chloride plus this. By the time you check the masses, hydrogen is 1, chlorine is 35.5, you have 6.5, sodium 23, oxygen 16, hydrogen 1, here is 40, 40 plus this. We worked on this already under the law of conservation of matter. You can go and see that very lesson. By the time you check everything out, you find out that the masses on both sides are equal to each other, and that's why it's called an equation. So for this, masses are balanced, while for the redox equation, masses and electrons, not only masses this time around. Masses and electrons are balanced. We're going to be explaining this better when it's time to work on this. So masses and electrons are balanced, while here only masses are balanced. So the very last difference we're going to be looking at today is simply this. Now, when it comes to balancing non-redox chemical equation, we use two major methods. So look at now simple trial, we call it trial and error, simple trial and error method, or the algebraic method, whichever we want to use there. Simple trial and error method or the algebraic method, either of this method is used. So you see that we use the trial and error method, whereby we're going to be adding coefficients. We're going to be assuming different coefficients. We're going to be adding them to some of them to the reactant and some to the product. So that's a simple trial and error method. Or we use the very best method known as the algebraic method. We're going to be seeing that in our next lesson. And why for redox equation complex, because this is simple, this complex. Now complex half cell, call it half cell, complex half cell, reaction method, half cell reaction method, or the ion electron method. This ion electron method is for far more complex redox equations. We're going to be looking at that. So we use complex half cell method or ion electron method, and all those methods are complex compared to the non-redox chemical equation. So at this very point, you're going to be drawing the curtain on this very lesson. You're done with the history and classification of various chemical equations. So now, next lesson, you're going to be looking at how to balance various chemical equations, starting with the non-redox, chemical equations. So if you found this lesson very helpful or resourceful, please subscribe to this very channel at Edu Mosaic, and please follow me also on Facebook at Revelation Hub, and share this lesson also with others. See you in the next lesson. Thanks.